When you think of welding, what comes to mind? Probably a blinding flash of light, right? Sparks flying, molten metal, but behind all that raw power, there's a world of high-tech science. It's this incredibly precise process that changes the very nature of metal, transforming separate pieces into a single, seamless, and unbelievably strong structure.
So what is that difference? What makes one weld strong enough for a skyscraper while another one fails without warning? It's not about just melting the metal hotter or faster. The real secret, it lies in understanding and controlling what's happening at the atomic level. It's the invisible science that we're going to dive into right now.
You see, on one hand, you could look at welding as just simple melting. You just fuse two pieces of metal together. But the reality is so much more elegant and complex. It's really a process of controlled metallurgy. We aren't just gluing metal together with heat, we are fundamentally rewriting its internal structure to create a bond that can actually be even stronger than the original material itself.
To really understand how we join metals, first we've got to take a quick look at how they're built. Because at a microscopic level, a solid piece of steel isn't just a uniform block, it's a highly organized crystalline world.
Okay, so at the very heart of every metal is this thing called a lattice. Just imagine atoms locked into a perfect, repeating, three-dimensional grid. This crystalline structure, this is the fundamental blueprint that gives a metal its strength, its ability to bend, and even how it conducts heat.
Now, these lattices don't just form one single gigantic crystal. As metal solidifies, countless tiny crystals, we call them grains, they start to grow. They expand outward until they just bump into their neighbors, creating this complex patchwork. And the boundaries where these grains meet, they are absolutely critical. They act like little walls that help stop microscopic slip and give the metal its strength. But of course, we almost never use pure metals for major structures. We use alloys. And you can think of it like a chef adding salt or spices to a dish. We add specific ingredients, these are the alloying elements, to a base metal. These new atoms dissolve right into the structure, creating a brand new material with tailored properties, like way more strength or resistance to rust.
And there are two main ways this happens. In what's called a substitutional alloy, the new atoms are pretty similar in size, and they just swap places with some of the original atoms in that lattice. But in an interstitial alloy, and listen up, because this is key for steel, much smaller atoms, like carbon, squeeze into the tiny gaps between the main iron atoms. This distorts the whole lattice and makes it much, much stronger.
All right, so now that we've got the basic structure down, let's introduce the real game changer in welding: immense heat. Heat is the tool that lets us manipulate and completely transform a metal's internal structure, and a lot of times we can do it without even melting it.
So here's a little puzzle for you. How can the exact same piece of steel with the exact same chemical makeup be made either soft and easy to bend or incredibly hard and easy to shatter? The answer isn't in the ingredients, but in the thermal recipe, how we heat it, and more importantly, how we cool it down.
The magic behind this is called a solid-state phase transformation. When you heat steel past a critical temperature, its entire atomic lattice suddenly reorganizes itself into a completely new structure, all while staying solid. This high-temperature phase is called austenite, and it's basically the gateway to unlocking all of steel's incredible versatility.
And once we've formed that austenite, the cooling rate becomes our control knob for the final product. If you cool it down slowly, the atoms have plenty of time to rearrange into a soft, layered structure called pearlite. Speed up the cooling, and you get something called bainite, which is a lot stronger. But if you quench it, cooling it almost instantly, you trap the atoms in this highly stressed, needle-like structure called martensite. It's fantastically hard, but it's also incredibly brittle.
This incredible power to transform steel with just heat and cooling, well, that is exactly what happens in the narrow band of metal right next to a weld. So let's zoom in on that weld and dissect the complex metallurgical world it creates.
You know, every weld actually creates three distinct regions. You've got the weld metal itself, that's the part that was fully melted. Then, far away, you have the original unaffected base metal. But the most complex and often the most critical region is the one sandwiched in between, the heat-affected zone, or haze for short. This is metal that got hot enough to transform, but never actually melted.
And the haze isn't even uniform, it's a gradient. As you move away from the molten weld, the temperature that the metal reached drops, creating these distinct little subzones. Right next to the weld, the intense heat makes the grains grow large and coarse, which can be a weak spot. A little further out, the temperature is in a sweet spot that actually refines the grains, making them smaller and stronger. It's like a microscopic timeline of heat's impact, all within just a few millimeters.
So, creating this complex landscape of zones is this incredible thermal balancing act.
And if that balance is off, if the metallurgy isn't controlled with absolute precision, this rapid heating and cooling can introduce some really devastating weaknesses that can lead to failure.
One of the sneakiest ways a weld can fail is through something called delayed cracking. This is when tiny hydrogen atoms, maybe from moisture in the air or on the steel, get dissolved into the molten weld. If that weld then cools too quickly and forms that hard, brittle martensite we just talked about, the hydrogen gets trapped inside. Then, over hours or even days, that trapped hydrogen builds up immense internal pressure until it literally cracks the weld from the inside out. So how do you prevent that? Well, you have to attack it from a few different angles. First, you've got to starve the reaction of its key ingredient, hydrogen. That means using special low-hydrogen welding rods and keeping everything super clean and dry. Second, you control the microstructure. By preheating the steel before you weld, you slow down the cooling rate, which stops that vulnerable martensite from forming and gives any hydrogen that did get in time to safely escape.
Another major enemy is hot cracking, and as the name implies, this happens while the weld is still screaming hot and solidifying. If you have impurities like sulfur in the metal, they get pushed to the very last pockets of liquid between the brand new grains. And these liquid films, they're like wet tissue paper. They have zero strength, and they get pulled apart by the shrinkage of the cooling weld, creating a crack just as the joint is being born.
So, preventing hot cracking is all about managing the chemistry. Step 1 is simple. Use cleaner materials with fewer impurities. For steel, metallurgists add a key element, manganese. It basically finds the sulfur and locks it up into harmless solid particles before it can form those weak liquid films. And for some stainless steels, they use an even cleverer trick, designing the filler wire chemistry to create a two-phase microstructure that acts like a microscopic ripstop fabric, physically blocking any tiny cracks from growing. So, after navigating all these potential disasters, how do we actually design a weld to be incredibly strong? Well, it turns out we use the very same metallurgical principles, not just to avoid failure, but to actively build strength right into the joint. Metallurgists have 4 main tools in their toolbox for this. First, the rapid cooling itself creates a very fine, interlocking grain structure that's naturally strong. Second, we use that solid solution strengthening we saw earlier by deliberately adding alloys to the filler metal. Third is transformation hardening. We control the cooling to get strong structures like bainite while avoiding that brittle martensite. And finally, for some special alloys, we can even use a later heat treatment to grow tiny, strong particles within the weld, which act kind of like rebar in concrete.
And this all comes together in this one really important concept, weldability. As this definition shows, it isn't just about whether a metal can be melted, it's a much bigger picture. It means the material, the welding process, and the structural design all have to work in perfect harmony to create a joint that will do its job safely for its entire lifespan.
So the next time you see a massive welded structure, a bridge, a skyscraper, anything, look past the visible seam. Think about the invisible world inside that steel, the lattices, the grains, and the carefully engineered microstructures. Because that, right there, is the unseen science, the controlled metallurgy that is truly holding our modern world together.